Hello students, so welcome to the series of lectures on digital speech processing. So in this video I am going to explain the classroom discussion topic on process of speech production. So in the previous video we have seen the brief introduction of the speech signal, how we can generate the speech signal and how we can transmit, how we can process, how we can store. So this we have already seen in the previous video. Now let us concentrate on this video, the process of speech production. So this is a lecture learning outcome. On completion of this lecture, you will be able to understand the process of speech production. So this is the signal processing flow. So just recall, this we have already seen in the previous video. Once you see once again. So information source, that is a human speaker, it's a lots of variability which be there according to the speech given by the speaker. And then immediately we'll be having the measurement of the observation, that is acoustic waveform of the articulatory positions, so neural control signals and everything that will be associated with this block. And coming to the signal processing. So in this signal processing, the signal representation is there and the transformation of the signal will be there. Okay. And after that, extraction and utilization of the information. Okay. So this can be done at the human business point of view, or we can also put a machine at the other end, so that whatever the speaker is speaking, the same thing will be reflected to the human listener. So this is the flow of the signal processing. Now coming to the representation of the speech signal, so this is the hierarchy of the digital speech processing. So broadly classified into the two important categories, one is waveform representation and other one is a parametric representation. So waveform representation which preserve wave shape through a sampling and quantization, and parametric representation which represents signal as an output of the speech production model. So again, we'll be focusing on excitation parameters and vocal tract parameters. So in excitation parameter, pitch, voice, unvoice, noise, transient, and so many other parameters also we are evaluating in the excitation parameter, and the vocal tract parameter, the spectral and then articulatory system. So this is the information rate of the speech. That means when you look into the parameter called the data rate, that is bits per second, the units. So there is a horizontal vertical line is also there, the dotted vertical line. So that is the separation of the two important representations. Waveform representation is there and then parametric representation is also there. So in the waveform representation, there is no source coding has been involved. But in the parametric representation, the source coding has been involved. Okay, so this is the analysis and synthesis methods we are going to be putting. So this is the speech processing applications. A wide variety of the application also will be available. So cell phones, voice over internet protocol, vocoders, that will come from the digital transmission and the storage. Okay, so which conserve the bandwidth. I clearly mentioned. So vocoder is the first important thing for in the year 1930 they have been evaluated. So the main advantage of the vocoder is that which conserves the bandwidth, encryption, secrecy, and the seamless voice and the data transmission that can be possible. And speech synthesis, messages, IVR, call centers, maybe that can be useful for them. And speaker verification, identification is the speech recognition, and then aids to the handicap, readings for the blind, speed up and slow down of the speech rates, and enhancement of the signal. So these wide range of the application that we'll be having. Now this is the speech tag actually. So when it comes to the lower part, that is the fundamental science and technology. For DSP theory, acoustics, linguistics, perception, everything we should evaluate. And then coming to the next one, the signal representations will be there. Temporal, short time spectrum, homomorphic and linear predictive analysis. Okay, but as far as our syllabus is concerned, we'll be mainly focusing on the homomorphic and the linear predictive. And coming to the processing algorithms. So how we can detect if we have any signal that we want to give. So from that signal, we want to detect what the speech and then silence. Okay, what is a pitch detection and then format analysis. That can be done actually. So in the application, coding application will be the synthesis recognition. So these many applications will be having. So this is a digital transmission and the storage of the speech. One of the most important applications of the speech processing was a vocoder. So voice coder was invented by Homer in the 1930s. So the purpose of the vocoder was to reduce the bandwidth required to transmit speech signal. So this is the schematic view of the vocal tract. Okay, so you can easily identify from the figure here in this slide. So how the speech production mechanism that can be possible, and we can easily see these are vocal folds will be there, and epiglottis will be there, timolum, and then nasal cavity, and then oral cavity, everything will be there. So what is the important point that you need to focus here is that air enters the lungs via normal breathing, the way how we are taking the breath. Okay, so this is a normal breathing we are taking. There is no speech at all. Okay, during the intake of the breathing. But when you see the second point of the slide, as air is expelled from the lungs, that means as the air is released from the lungs via the trachea or windpipe, we can call. So the tensed vocal folds. So here we'll be having the vocal cords within the larynx. So larynx is nothing but, you can understand, like, which is the speech toolbox. Larynx is the speech toolbox. So which are caused to vibrate by the airflow that is coming from the lungs. Okay, so as air is released from the lungs via the trachea or the windpipe, and the tensed vocal cords within the larynx will vibrate, so that the sound will come. Okay, so that way you need to understand actually. So this is a anatomy of the vocal tract, how we are going to be producing the speech. Okay, and the pressure of the airflow that will be given to the intensity of the speech that you are going to be generating. Okay, so particularly speaking, we have considered this the vocal cords. Actually, this is a schematic. Okay, and we can also understand the way how I have mentioned here. So the air flow from the lungs through the trachea, and that will transmit it to the vocal tract. So that is the shape of the vocal tract, and the length of the vocal tract is also different for men and then women. Okay, the length of the vocal tract for men will be larger, and the length of the vocal tract for women will be lower compared to the men. So this is the way how we need to understand the air flow from the lungs, and these are vocal cords. So which is closed now. When it is closed, there is no air passes to it. Okay, when it is open, then the air will be flows. So actually, this is an oscillator we can call. The vocal cords forms a relaxation oscillator. Okay, so first of all, so it is closed like this, and the air flow is coming from the lungs, and as it is closed, there is no air is going to be entering into the vocal tract. The moment when it is going to be open like this, the air will flow, and obviously the speech and the sound will come. Okay, so that way you need to understand. Okay, so vocal cords is forms like, it's just like an oscillator, opening and closing, opening and closing. So that will be simultaneously happen. So this is an abstraction of the physical model you can easily understand from this figure. So this is the lungs, the muscle force, and here the mechanical oscillator is a form. So this is the spring and mass will be there. Okay, this is forms like a oscillator, the mechanical oscillator. Okay, so here opening and closing, that should be depends upon the airflow, and the vocal cords will be open, the air will be flows, and accordingly the whatever the speech that you want to convey to the other person, that will be comes through the lips. Okay, and you can also see this is the speech signal that will be available. Okay, now we need to estimate how much of time period for a corresponding speech signal that we have pictorial representation from that. Okay, and when it comes to the filter analysis, we can also assume that the time varying filter is nothing but it is a vocal tract. Okay, the filter we are considering as a vocal tract. The filter specification that should be suitable to the vocal tract. Okay, and this is an excitation. So excitation that comes from the vocal cord. Okay, so from the vocal cord, whether we speak anything, so that will be comes as a voice signal. If you don't speak anything, that's an unvoice. There could be mixed voice and unvoice signal. That is an excitation generator, we call it vocal cord. So through that is an input will be given to the filter, and the filter output will be the speech signal. The speech is a combination of both voice and unvoiced signal. So that way you need to understand in a system. So as a system, we are representing the vocal tract like this. So these are some of the example of the speech waveforms you can easily understand from this figure. So this is the silent signal. Okay, so S represents the silence. So background, there is no speech at all. Okay, it's a background, there is no speech at all. And when you see here, this is silence is there, unvoiced is there, and the voice signal is also there. Okay, so for unvoiced, there is no vibration in the vocal cord. Okay, if there is no vibration in the vocal cord, means the vocal cord is in closer position. There is no air coming from the lungs to the vocal cord. Okay, And this is a voice signal. Voice means that is a quasi-periodic speech. Okay, that we already know, which is a slowly time-varying signal. Okay, so like that, so several different waveforms you can easily understand from this. So this is a complete voice signal. The last figure is a complete voice signal. There is no unvoiced, there is no silence at all. Okay, so this is the pictorial representation of the speech signal. Thank you, students. Thank you for watching this video.